Okay, second video on volumes by cylindrical shells. So last time we had developed the formula for that, which is, remember, that's basically integrating the circumference of the shell times the height of the shell times the thickness of the shell. The circumference is going to be determined by 2 pi times the radius, whatever the radius happens to be, and we'll see that it can change just a little bit, but in general, it'll be an x or a y value. Times the height. The height is going to be given as the function, whether it's an f of x or f of y, depends on how we're evolving the section. And then dx or dy will simply be the thickness or the change of the radii, which again we want to be really small when we integrate. So let's take a look at our first example. We're going to go ahead and take the equations given here and use the method of cylindrical shells to find the volume generated by rotating the given region bounded by the curves about the y-axis. So it's pretty much like the example that we were just talking about, just a little bit different functions here. So the first thing I want to do is I'm going to go ahead and sketch what this thing kind of looks like. So y equals x cubed without that little crinkle in there looks like that. Y equals 0. Again, I probably should have used different colors for this, but y equals 0 is here, x-axis. X equals 1, x equals 2, so x equals 1, x equals 2, something like that. So it looks like our bounded region is this right here. Now, to be completely honest with you, this would not be a difficult one to do using even the washer and disk method. You would have to make a change. You'd have to do 2 different integrals because the radii are going to change. And I'm going to erase this part here, but the radii are going to change when you're using this function, and then all of a sudden down here it's that vertical line. So from that perspective, you would have to do 2 separate integrals, but it could be done. It would not be that difficult to do. In this case, it's actually going to be quite easy. So we are going to revolve it around the y-axis. And if we do that, what we're going to get is something that looks like this on the other side. Whoops. Wrong color. And then it looks like maybe about right here. And then like that. And then when you go ahead and revolve this thing, you're going to get something which is kind of circular there at the top. Looks something like that. So that's what your shape would look like, something like that. All right. It's kind of a bowl with a bottom that's kind of hollowed out and cylindrical. I guess that's the best way to look at it. So the idea is, in order to find the volume by actually creating shells here, because this is what we have, this first one right here is actually a cylinder. And then every piece from there on out, we're going to add cylinders to the outside of this thing. The volume would be given by, well, first of all, where does the cylinder start? This whole inside piece, let's see, yeah, let's do this. This whole piece right here has been hollowed out. Okay, there's nothing there. So the cylinder itself doesn't actually start until we get to 1. So I'm going to integrate from 1, and then the cylinder is going to stop at 2, because that's where the function stops being rotated. So we're going to go from 1 to 2. The circumference. The circumference of this thing is going to be 2 pi r, but r is the radius. The radius always goes from the axis of revolution out to wherever it's going to stop. Well, in this case, remember, the radii are going to go from here out to here, out to there, out to there. Those are all x values, whatever they are up until I get to 2. So that's 2 pi x. The height is given by the function itself. The function here is x cubed. So the height is x cubed. So here's our circumference. Here's our height. And then the thickness, because we're doing this around the y-axis and we're counting left to right, the change of the radii will be a dx. That should always match whatever variable you have anyway. So now we can go ahead and actually take the integral here. So let's see, 2 pi is a constant. That comes out to the front. This should be relatively simple, I would think. X times x to the third is x to the fourth. Yeah, this will be an easy one to integrate. So 2 pi antiderivative is going to give us 1/5 x to the fifth, and we'll evaluate that from 1 to 2. So the constant is 2 pi fifths. Plugging in 2 and plugging in 1 and subtracting 2 to the fifth is, let's see, 2, 4, 8, 16, 32 minus 1. So it looks like I'm going to get 31 times 2 pi fifths. 31 times 2 is 62. So we're going to get 62 pi fifths. That's our volume. All right. Let's try another one. So again, we're going to use the method of cylindrical shells to find the volume generated by rotating the given region bounded by the given curves about the y-axis. So again, we're going about the y-axis, which is great. Let's sketch this. All right, in order to sketch this, I'm going to have to do a little bit of work here. 4x minus x squared, that is a parabola which opens down because the x squared is negative. I should probably find the x-intercepts, and to do that, 4x minus x squared, we'll set that equal to 0, factor out an x. So it looks like our zeros are going to be 0 and 4. 0, and we'll just put 4 out here. And I really don't care exactly where the vertex of that thing is, but it's going to look something like that, close enough. And then y equals x, of course. Standard y equals x line. So it looks like my bounded region is right here. Okay, that's the bounded region right there. So that's going to be revolved around the y-axis. So if I kind of sketch what that looks like on the other side, mirroring that, something like that. So now I can get rid of this stuff right here. So that's kind of what it looks like on the other side. So I'm going to have a bunch of circles, one at the top, and then circles all the way down to the bottom. A bunch of shells that looks like that. And it looks like I'm going to have, like I said, a bunch of shells. So kind of go down, there's a shell, something like that. And then the bottom of the shell. There you go. A bunch of shells. The top one's not drawn very well, but it still does create a shell. So, same idea, same principle. Volume. Remember, the volume of a cylinder is going to be 2 pi r, which is the circumference of the cylinder, and r again, because we're going around the y-axis, is going to be an x value out to wherever it is, so it's 2 pi x. This time, our function is going to be a little bit different. Our f of x is a little bit different because I actually have two functions here. Got the upper function and the lower function, and I'm talking about the shaded area or the highlighted area in here. So in this case, it's going to be the upper function minus the lower function. The upper function here, of course, is the parabola minus the lower function, which is the linear function. So it's going to be 4x minus x squared minus x dx. And then the important other piece of information is, where do I integrate from? Should be pretty clear that this one here starts at 0 and goes out to this intersection point right there. So if you're not exactly sure where the intersection is, what you can always do is set the two equations equal to each other and then figure out the intersecting points. So subtracting x on both sides gives us 3x minus x squared equals 0, factoring out an x. So it looks like my intersections are going to be 0 and 3. All right, now I've got everything that I need to do to go ahead and find the volume. So the volume here is going to be the integral from 0 to 3. Actually, let's go ahead and take the 2 pi out to the front. Let's see, simplifying this, 4x minus x on the inside is going to give me 3x, but I have to distribute the x out on the outside through, so that's going to be 3x squared minus an x cubed dx. All right, antiderivative won't be hard. Might be a little messier here with the values, but let's see. 2 pi times, let's see, antiderivative of 3x squared is x cubed. Anti of x cubed is 1/4 x to the 4th, and we'll evaluate from 0 to 3. Fortunately, plugging 0 in is going to give us nothing, so really it's going to be whatever we get when we plug the 3 in. So 2 pi, 3 cubed is 27. 3 to the 4th is 81, so that'll be 81/4. Let's see, combining those like fractions, we're going to have to make 27 into terms of fourths. So that's going to be, what is that, 54, 108 over 4 minus 81/4. 108 minus 81 is 27. So we get 2 pi times 27/4. Whoops, should have made a bigger parentheses there. And so that should give us 54. No, that's not right. That's going to give us, let's see, 2 over 4 reduces to 1/2, 27 pi over 4. There we go. That's our volume. All right, let's try and change it up. 2 more examples. Use the method of cylindrical shells to find the volume generated by rotating the given region bounded by the given curves about the x-axis this time. So if we're going to find this bounded by the x-axis, revolving around the x-axis, we're going to need to solve every one of our equations in terms of x equals something where the function itself is y. So let's go ahead again and kind of do a sketch first. See what's going on. So y equals square root of x looks like this. Bounded by x equals 0, which is the y-axis. That's kind of funny, it jumped at the same place. Y equals 2, which is going to be some kind of a horizontal line up this way. So here's y equals 2. And this one right here was y equals the square root of x, but we're going to want to solve that in terms of x. So let's go ahead and do that. Squaring both sides is going to give us x equals y squared. Same equation, just written in a different way. So there's our region. And this is the shaded area, or the highlighted area, that we're going to revolve. And we're going to revolve that around the x-axis. So around there. So let me see if I can give us a good sketch of what this will look like. It's going to be something down here. And then it looks like we're going to be curved from there. Something like that. And then my shells will look something like that. And then, of course, the shell goes down like this. There's a cylindrical shell that just happens to be turned to the side. So as you can see, the thickness now, right here, that's a dy. The thickness is in terms of y. So, same general idea. The volume, we're going to integrate. It'll be a 2 pi r. This time, however, the r, the radius, is that way. And remember, the radius goes from, the radius is going to go from the center, or the axis of revolution, out to whatever it is. Remember, these are all y values now. Whatever it happens to be, it's a y value. So it's 2 pi y. We're not interested in writing the function in terms of y. We just know that it's a y value. The height of this goes this way. Well, the height is going to be that function in terms of x equals y squared. So the height is y squared. Remember, it's turned on its side now. And then the thickness, like we said, the thickness down there in that black was delta r, or in this case, it's going to be the change in y, or dy. All right, so this one ends up not being too difficult, I believe, numerically to do. Only other thing we have to figure out is, what am I going from? Well, this one starts at y equals 0, right here, and goes up to y equals 2. Okay, the entire thing is covered there. So from 0 to 2. All right, let's see what we get. Pull out the 2y to the front. I'm sorry, the 2 pi to the front. Y times y squared is y cubed dy. This one should, again, be relatively simple. 2 pi times antiderivative 1/4 y to the 4th from 0 to 2. Pulling the 1/4 out to the front with the constants, 2 pi over 4 is the same thing as pi halves. And then plugging in 2 and 0 into y to the 4th will give you 16 minus 0. So we're going to get 16 pi halves, or 8 pi. And that's the volume. All right, so that's one where it's done with respect to revolving around the x-axis. All right, last one. This one's got a little bit of a change in it, a little bit different. So let's take a look at what this thing looks like. So we are going to revolve this one around the specified axis. Okay, it's going to be bound by the curves around the specified axis. So it looks like we've got the curves y equals square root of x, y equals 0, x equals 1. Let's go ahead and at least sketch the region first. Let's see what we've got. Y equals square root of x. We saw that one before. Y equals 0. That's the x-axis. And x equals 1. Okay, x equals 1, we'll put right here. Y equals 0, right there. So here's our region that we're going to revolve. But here's the difference. We're revolving this region around the line x equals -1. Well, that's out here. That's our axis of revolution, which means, put our little arrow there, that's what we're revolving around. There's going to be a large space in between. So when I go out there, I'm going to have to go another unit over here, start there, and go out that way, and then looks like I'm going to curve this thing up and then back down. So my shells are going to be relatively large here compared to the last ones. Looks like the shell, here's the inside, and then there's an outside. That's a big shell. I kind of missed. Here's your shell. There's your cylinder, all the way down to the bottom. Okay, this is going to create a small difference in what we're doing. Idea is still the same. Circumference is going to be a little bit different. Alright, so the volume. We are going to integrate. We've got to do 2 pi r for our circumference. 2 pi is always 2 pi, so there's no problem there. The radius, however, remember that the radius is going to be, in this case, it's going to be some kind of an x value. However, the radius is not going to just be x. If it was just x, it would be measured from here out to wherever my shell is, or out to wherever my shell is. But the radius of these circles, or cylinders, comes from the axis of revolution all the way out here. Well, the axis of revolution was around the line x equals -1, which means that this distance has a space of 1 that we have to add on to the x. So my actual radius here is x plus 1. So when I go to plug this in, that's my radius. So 2 pi r in this case is x plus 1. I have extra space that I have to account for. The height, now the height is just going to be the function, which is the square root of x. And then it's going with respect to all x values, so the thickness of each one of those shells is a dx. Alright, so that was the hardest part, was figuring out that radius. When we've shifted something off of being rotated around only the x or y axis, because you have to remember the radius is always measured from the axis of revolution out to the function. Okay, so let's go ahead and finish this one off now that we've got that part. Oh, we need to figure out where it's going from first, don't we? So it looks like this one's going to start at 0 and go out to 1. That seems actually pretty straightforward. Starts at 0, goes out to 1. We're good there. Zeros and ones are wonderful to deal with integrals, by the way. Okay, simplify. Let's see, volume equals 2 pi on the outside. Integral from 0 to 1. We're going to have to distribute that x plus 1 in the square root of x. So x times the square root of x. Square root of x is x to the 1/2. So we're going to multiply that and get x to the 3/2. And then 1 times the square root of x is just x to the 1/2 dx. All right, it's going to definitely give us some fractional values here. 2 pi antiderivative x to the 3/2, so that's x to the 5/2, so 2/5 x to the 5/2. X to the 1/2 is going to be x to the 3/2, so 2/3 x to the 3/2 from 0 to 1. So again, plugging in a 0, fortunately, isn't going to do any good, so we'll plug in the 1 and see what we get. 2 pi plugging in 1, 1 to any power is 1, so 2/5 times 1 is 2/5. 2/3 times 1 is 2/3. And again, if I plug 0 in, it becomes 0, so subtracting 0 would be done. So we're going to have to put these in terms of 15ths. So that's going to be, let's see, multiplying by 3 top and bottom gives me 6/15. Multiplying by 5 top and bottom will give me 10/15. So it looks like in the inside I'm going to get 16/15 multiplied by 2 pi will give us 32 pi over 15. And that's the volume. Alright, about 26 minutes of video on the second video here. You should have plenty enough now to go ahead and do the 4 problems that you guys were given for the volume of cylindrical shells.